Hi, I'm Rui from Vassar College in New York. I'm going to present geolocation-based sector selection for Vehicle to Infrastructure 802.11 AD communication, a work performed in collaboration with colleagues from Instituto de Telecomunicações in Portugal. 802.11 AD is a Wi-Fi standard that uses unlicensed spectrum in the 60 GHz region, known as millimeter wave. The wide 2.16 GHz channels available in this region enable very high data rates of up to almost 7 gigabit per second. However, the high 60 GHz region frequency range causes very high attenuation, particularly in non-line-of-sight conditions. Therefore, if traditional omnidirectional antenna patterns are used, the communication range can be quite short. To combat this, 802.11 AD uses directional communication, meaning it focuses its transmission power on a narrow beam directed at the receiver, thus improving communication range. 802.11 AD was designed for home and office use, where nodes are mostly static, which facilitates the establishment of directional communication. Vehicular communication, on the other hand, features a high degree of mobility, making directional communication much harder. Still, its very high data rates make the use of AD very enticing. Can we optimize the way in which it achieves directional communication for use in a vehicular context? We shall see. 11 AD devices feature a phased antenna array. Directionality is achieved by varying the individual gains of the antennas in the array. This is done in two phases. First, the device picks one out of a number of predefined antenna configurations. Then, in a second phase, which is optional, antenna gains can be fine-tuned by reacting to feedback from ongoing communication. Our work focuses on the first phase, sector selection. Sector selection is done by performing a sector-level sweep, or SLS, which involves two nodes and operates as follows. The initiator node begins by sending a frame using each of the sectors available, while the responder listens in omnidirectional mode. Then it's the responder's turn to send the initiator a frame using each of its possible sectors. These frames will carry feedback for the initiator in the form of the ID of the sector that yielded the strongest signal at the responder. That will be the sector that the initiator uses from then on. The initiator returns the favor by sending the responder a feedback frame identifying the sector that the responder should use to maximize the signal strength at the initiator. Thus, at the end of this process, both initiator and responder know which sector to use. With this in mind, we pose the following research questions. First, how well does 802.11 AD sector selection perform in a vehicle-to-infrastructure communication scenario, where the vehicle is mobile? Second, we investigate whether network performance can be improved by using geolocation for sector selection. Our intuition is that since location encodes distance, angle between communicating antennas, and the presence of obstacles, it may be a good heuristic for sector selection. Therefore, instead of performing a sector-level sweep to pick a sector, we could perhaps just use the sector that has statistically performed the best for the current location. In order to answer these questions, we conducted a measurement campaign using consumer off-the-shelf 802.11 AD devices in a vehicle-to-infrastructure setting. Data was streamed from an access point placed at the corner of an intersection to a mobile vehicular client. Two different client mobility patterns were used. In the first, the client drove slowly, i.e. at walking pace, in a single direction. For example, west to east or east to west. In the second, the vehicle drove at normal road speeds in a circuit that allowed it to pass by the AP in every possible orientation. Analysis of the collected data revealed two inefficiencies in the sector selection process. First, the majority of sector-level sweeps were inconsequential, meaning they produced no change in sector being used. This was the case for 82% of SLSs initiated by the AP and 65% of those initiated by the client. This leads us to conclude that the number of sweeps performed was unnecessarily high. Second, we found hopping between pairs of sectors, or ping-ponging, to be common. In fact, 25% of free sector sequences are of the form S1, S2, S1 again. The return to the original sector is often very quick, occurring in 10 milliseconds or less, 35% of the time for the AP, and 60% of the time for the client. Therefore, it is questionable whether a good percentage of these sector changes are indeed justifiable. Let us now focus on whether we can improve upon this by performing sector selection based on geographic location. Our proposal is as follows. First, nodes should create a historical record of their sector use. In order to do this, they would start by discretizing space into square cells, for instance of 1 by 1 meters, in order to enable spatial data aggregation. Then they would create a record of what sectors have been used from each particular cell. For example, sectors 1 and 2 have been used from this pink cell over here. For each cell and sector combination, we would then record the length of time spent communicating at each different data rate. In this example, we have that sector 1 was used during 1 second at 100 megabits per second and 2 seconds at 250 megabits per second. Sector 2 was used for 1 second at 600 megabits per second and 9 seconds at 100 megabits per second. Once this historical performance record has been established, we can choose the statistically best sector for any given cell by computing the expected average data rate for each of the possible sectors. In this example, that would yield 200 megabits per second for sector 1 and 150 for sector 2. That being the case, we would pick sector 1 as the sector to use anytime we are in this particular cell. The key assumption underlying this strategy is the stationarity of the distribution of achievable data rates as a function of sector and location combination, i.e., that the likelihood of a sector being able to achieve a certain data rate from a particular location doesn't change in time. We evaluated the performance of our proposed strategy against the default 802.11 strategy by computing the throughput gain, meaning that we are focused on maximizing the amount of data that can be transferred per unit of time. We did this by performing the following procedure for each cell. First, we took note of the amount of data that was transferred to and from the cell in the experimental data that we've collected. Then, we computed the amount of time that was spent communicating while the client was on that particular cell. Because our proposal does away with sector-level sweeps, we included that time here. In this particular example, we have a total of 1 plus 2 plus 1 plus 9, which gives us 13. Then we pick the sector that maximizes the expected average data rate, which in this case is sector 1, and take note of that rate, which is in this case 200. Now we can compute the amount of data that could have been transferred if we had used the best sector all the time, by multiplying the time by the expected average data rate. In this case, we multiply 13 by 200, giving us 2600 megabit of expected data transfer. Finally, we can compute the throughput gain as the amount of additional data that we can transfer using our new sector selection divided by the original amount of data. In this example, we have an additional 500 megabit of data divided by the original 2100, giving us a gain of 23.8%. Because we pick the sector that maximizes the expected data rate, the proposed scheme is optimal given our chosen evaluation metric. We also considered the following two alternatives as comparison points. A random strategy where we pick a sector uniformly at random from those that were used in that particular cell, and median SNR, where we pick the sector with the highest median historical signal-to-noise ratio. The choice of SNR is motivated by its common use as a channel estimator and correlation with achievable data rates. Here we have the empirical cumulative distribution function, or ECDF, of the throughput gain for the three different sector selection metrics under study. This particular plot shows the results when we discretize space into cells of 1 by 1 meter. Our proposed optimal selection scheme outperforms the default strategy for almost all cells. This confirms that there's room for improvement upon the default strategy when 802.11ad is applied to a vehicular context. However, large gains of over 10% are only achievable in a minority of cells, in this case 25%. Interestingly, the median SNR metric underperforms the optimal strategy significantly. In particular, for some cells, it decreases performance relative to default even more than the random strategy. When we increase the size of the cells from 1 by 1 to 5 by 5 meters, the long tail, where a small number of cells experience a large throughput gain, disappears. This makes intuitive sense since the larger the cell is, the larger the diversity of antenna angles and line-of-sight obstacles that fall onto a single cell. These heat maps show the throughput gain resulting from the three different sector selection strategies for each individual cell. It's interesting to note that cells aligned with the side and the rear of the access point experience the highest gains. We can also observe that communication towards the east was difficult. We suspect this to be related to the site's elevation profile. In summary, we can conclude that off-the-shelf 802.11ad sector selection is inefficient when used in a vehicular context. The majority of sector-level sweeps are inconsequential, meaning they don't result in a sector change, and when there are changes, they often result in ping-ponging between two sectors. Our proposal is to instead choose the statistically best sector for a given location. Our results show that this can yield substantial gains for around a quarter of spatial cells. Additionally, performance was shown to be positively correlated with localization granularity. This means that localization accuracy plays an important role in the feasibility of the proposed scheme, which is something that we plan on studying in the future. Thank you.